already seen the quantum mechanical problem of a particle in a box. Now, while a box whose walls have infinite potential might be a good approximation for some systems, of course in nature we don't actually have infinite potentials. Today we'll consider a particle in a finite potential well. Classically, if the particle's energy is less than the potential height, the particle can't escape the well. However, quantum mechanically the story is more interesting. Consider the following problem. Consider a particle in a 1D potential well of height u and width L. The particle has energy E less than u. Schematically draw the wave functions for the ground state and first two excited states of this system. How far beyond the walls does it take the wave function to decay to 1 over e of its value at the walls? We'll start by writing the form of the wave function in each region of the well. The spatial part of the wave function solves the time-independent Schrödinger equation, which I've written here. In the middle of the well, in region 2, the solutions to this equation will be oscillatory. This is the place where u equals 0. So we can write these solutions as sines and cosines. I'll write them in the form b cosine kx plus c sine kx, where k just comes from plugging this into the Schrödinger equation equals root 2me, e the energy of the particle, over h bar squared. And again, in this region, u equals 0. In the outer regions of the box, regions 1 and 2, the solutions to this equation are exponentials, growing and decaying exponentials. And that's because the potential u is greater than the energy of the particle. In region, so I'll write in general psi of x. These solutions will look like a e to the alpha x plus d e to the minus alpha x, where here, where u is non-zero, alpha will be root 2m u minus e over h bar squared. So in the first region of the box, we need the wave function to go to 0. We need it to be finite at large negative distances. So only the growing part of the of this wave function will contribute. So in order that the wave function be normalizable, only this term will contribute on the left-hand side of the box. And for the same reason, on the right-hand side of the box, since we need the wave function to go to 0 at large distances, we need it to be finite at large distances. We can only have the decaying exponential piece here. So in region 3, we'll have a equals 0, and this will be the only case. Okay, so next we need to determine these constants a, b, c, and d by imposing continuity of the wave function and its derivative at x equals minus L over 2 and L over 2. So we need to use the matching conditions. I've written all of these conditions in the attached PDF, and I'm not going to write them here. But the important feature that comes out of writing these matching conditions is the following. There are two kinds of solutions. There are even solutions, by which I mean psi of x equals psi of minus x. And for these even solutions, since cosine is an even function, c equals 0 and a equals d. So these are of the form in region 1, psi equals a e to the alpha x. In region 2, it goes like the cosine. And in region 3, it goes like a e to the minus alpha x. This is in regions 1, 2, and 3. And the other type of solution that comes out of solving all of the continuity conditions are odd type solutions, by which I mean psi of x equals minus psi of minus x. So for the odd types of solutions, we'll have a equals minus d. in regions 1 and 3. And we'll only have the sign part in the middle. So these will look like, I'll call it d e to the alpha x in region 1, c sine kx in region 2, and minus d e to the minus alpha x in region 3. So actually, it had to be the case that we could only get even or odd solutions for this system, and that's because the potential itself is symmetric about x equals 0. The potential satisfies u of x equals u of minus x. It has the symmetry about the center of the well. And this actually implies that we could only get even or odd solutions like this for the wave function. Other conditions that come from solving these continuity equations are the following. For the even solutions, we would get alpha equals k tangent kl over 2. And for the odd solutions, we'd get a similar equation, alpha equals minus k cotangent kl over 2. Good. So these are conditions that involve the energy E. Remember, alpha and k both involve the energy E. And then solving these continuity equations gives us relationships between A and B in the even case and C and D in the odd case. And then normalizing the wave function will determine the final constant. So everything will be determined by solving these conditions. Now, these green equations I've written here in terms of E actually give the quantization condition on the energy. So you remember in the normal particle in a box scenario, the energies are quantized. They're labeled by the quantum number n that runs from 1, 2 on up. And that comes from solving the continuity conditions on the wave function and its derivative. Here, we similarly get quantization conditions on the energy. They're just a bit harder to solve. So solving these equations for the quantized energy levels involves graphical or numerical techniques, and I'm not actually going to do that here. But we already have enough information to schematically draw the wave functions. We know that they're going to be quantized. The energy levels are quantized, labeled by the quantum number n. And we know that there are even and odd type solutions. So here I'll draw the forms of the wave functions. I'll draw psi for the ground state as a function of x. These boundaries correspond to x equals minus L over 2 and x equals L over 2. The first excited state labeled by n equals 2, and the third excited state, or the second excited state labeled by n equals 3. So the ground state will have no nodes, and this is a general feature in quantum mechanics. The ground state has no nodes, and the more nodes in the wave function, the higher the energy level it corresponds to. So this state will be an even solution. So we'll start with the growing exponential. It'll match onto a cosine function with no nodes. And then that'll match on to the decaying exponential, like this. The first excited state will have one node, and that'll be, therefore, an odd type solution. So the growing exponential will match on to a sine function with one node. We'll match on at L over 2 to the decaying type solution, but with the minus sign because these are odd type solutions. And then similarly, when there are two nodes, we'll again be back at the even case. We'll have a cosine-like function with two nodes, which will look something like this, and so on for higher energy levels. So this answers the first part of the question. The next part of the question asks about the length after which the wave function decays to 1 over e of its value at the wall. So that's its value right here. And we're going to call its length, this length, delta, it's called the penetration depth. And the physical meaning of delta is that the probability of finding the particle outside of the well, the classically allowed region, is only appreciable to within about a distance delta of the edges of the well. So we can solve for delta by using its definition. So we want to know when the wave function is 1 over e times its value at the wall. So for instance, for the right-hand side of the wall, which by symmetry will give us the same answer as the left-hand side of the wall, the value at the wall is just e to the minus alpha times x equals L over 2 times the normalization. So for instance, for the even case, let's say A, we get the same answer for both the even and odd cases. And so by the definition of delta, the wave function is at this value at x equals delta plus L over 2, since we want to measure delta from the edge of the wall. So that's the wave function being, again, A, so these normalizations will just cancel out, which is why I said it didn't matter whether we considered the even or the odd case, times e to the minus alpha times delta plus L over 2. And we can use this relationship to solve for delta, which I do in the attached PDF explicitly. And the result is delta equals 1 over alpha, where recall alpha goes like the square root of the potential height minus the energy of the particle. So this goes like 1 over root u minus e. So what we've learned is that when the potential height of the well is much larger than the energy of the particle, so this denominator is then very big, and then delta is very small. So there's a very small chance of finding the particle outside the classically allowed region. So as u approaches infinity, in particular, I'll go to 0 chance of finding the particle outside the allowed region. However, as the energy of the particle gets closer and closer to the height of the well, delta will get larger, and there will be a larger chance of finding the particle outside of the well. There's a simple way to think about these results, and that's in terms of the uncertainty principle. Classically, we said the particle can't make it outside of the well. However, because of the uncertainty principle, it's possible for the particle to borrow some energy and take a trip to the other side. So if I estimate the lower bound on delta t, delta e, as about h bar from the uncertainty principle, this is greater than or equal to h bar over 2, and I could say that the particle would need to borrow an energy of u minus e plus a little bit extra, so it has some kinetic energy, to venture out to the other side. But the more energy I want to borrow, so the farther I want to go out past the boundary of the classical region, the less time I have to return it. So the faster I have to move back to the classical region so that I'm not caught with my hand inside the cookie jar, so to speak. So I can only venture so far out of the classical region. So the faster I have to move back to the classical region so that I'm not caught with my hand inside